To manage diabetes effectively, patients need continuous, instantaneous data about their blood glucose levels. That requires converting a biochemical reaction inside the body directly into a reliable electrical signal on a monitor. In a perfect ampermetric biosensor, the target molecule would react right at the surface of an electrode, immediately giving up or taking in an electron to create a measurable current. The standard biological catalyst we use to break down glucose for these measurements is an enzyme called glucose oxidase. Glucose oxidase is highly specific, but its actual reaction center, the active site where the electron exchange happens, is buried deep inside the enzyme structure. Surrounding the active site is a thick protein shell, acting as a strict electrical insulator. Electrons generated deep inside face massive physical resistance. They simply cannot jump the wide gap across this shell to reach a standard metal electrode. Because of this barrier, placing an unmodified enzyme directly against a metal contact is highly inefficient. It generally fails to produce enough current to be useful in a clinical device. Older sensor designs bypass this problem by flooding the area with free-floating chemical mediators that ferry electrons back and forth, but that diffusion process is inherently slow. To create a faster, more responsive sensor, we need to completely bypass the insulating shell and extract the electrons directly. We need to physically wire the enzyme's reaction center to the electrode surface. This requires constructing a microscopic conductive bridge, a solid structure that can either penetrate the protein shell or tightly envelop it to capture the charge immediately. Achieving this direct, solid-state electrical communication between the enzyme and the electrode is the defining characteristic of a third-generation biosensor. By abandoning liquid chemical diffusion, engineers shifted the problem from chemistry to solid-state material science, focusing on creating anchored conductive polymers. The first major breakthrough in establishing this direct connection was the development of the electron-conducting redox hydrogel. The foundation of this architecture is a water-soluble polymer chain, typically polyvinyl pyridine or PVI. Looking at this diagram, we see a crucial modification to the polymer backbone, the covalent attachment of specific redox mediators. The active nodes tethered directly to the polymer rings are osmium-based complexes, which transition reversibly between a 2+ and 3+ charge state. When these engineered polymers are applied to a sensor electrode, they become insoluble. However, they retain the ability to swell significantly when exposed to an aqueous environment, like blood or interstitial fluid. As the hydrogel matrix swells, it permeates the space around the glucose oxidase, completely enveloping the insulating protein shell. Because they are suspended on flexible tethers within the gel, the localized osmium centers are mobile. They physically swing and collide with one another in a rapid chain reaction, passing electrons outward from the enzyme. These collisions act as a network of microscopic stepping stones. They extract the charge and wire the deep active site to the electrode, regardless of how the enzyme is physically oriented within the gel. While hydrogels use tethered atoms, a second approach to third-generation wiring utilizes electrically conducting organic salts. This diagram shows the specific molecular structures used in this method: TCNQ, which acts as the electron acceptor, and TTF, the electron donor. When these two molecules are paired, they form a highly conductive unit known as a charge transfer complex. This approach offers significant manufacturing simplicity. An active, wired electrode can be prepared simply by dipping the conductive salt layer directly into an enzyme solution. Once integrated, these organic conductors remain highly stable over time because of how they interact with the enzyme's hydrophobic outer environment. The alternating positive and negative charges of the organic salts align with opposing charges on the protein shell, forming strong physical connections known as salt links. These strong physical bonds ensure the enzyme remains tightly anchored. The organic salt matrix provides a stable, easily manufactured alternative to complex hydrogels, achieving the same direct electron extraction. We can take these individual wiring techniques and scale them up to build the macro architecture of a complete biofuel cell or closed-loop sensor. This schematic illustrates a fully integrated biological electronic matrix. Looking at the anode side on the left, the primary structural wire isn't a flat metal plate, but a dense matrix of carbon nanotubes interwoven with the glucose oxidase enzymes. As glucose is oxidized, the electron pathway flows immediately from the wired enzyme into the highly conductive carbon nanotube scaffold. Over on the right side at the cathode, the system uses a complementary enzyme, lacase, embedded in its own identical carbon matrix. The circuit completes itself here. The transferred electrons are consumed by the lacase to reduce ambient oxygen directly into water. By packing the enzymes tightly into this conductive nanostructure, the entire reaction happens internally. It creates a closed, rapid electrical circuit without losing charge to the surrounding fluid. Designing these complex matrices requires immense molecular precision. So why go to these extreme lengths when older glucose sensors were already functional? This diagram compares the 3 generations of amperometric biosensors. The first generation measured hydrogen peroxide, which had to physically diffuse to the electrode. The second generation improved this by using free-floating mediators, like ferrocene, to shuttle electrons. Both of these older designs were bottlenecked by the same physical limitation. They relied on the slow, random diffusion of molecules through a liquid space to carry the signal. The ultimate advantage of the third-generation design is thermodynamic. Extracting electrons directly through a solid wire bypasses the massive energy losses associated with fluid diffusion. We can see this in the required operating voltage. A first-generation sensor needs a high potential of plus 0.68 volts. Second generation drops that to 0.19. By wiring the enzyme directly, the third generation bottoms out at a highly efficient plus 0.10 volts. Operating at this minimal voltage is critical. It is low enough to avoid oxidizing other compounds present in human blood, which prevents false signals and electrochemical interference. For the patient, that lack of interference translates directly to a highly accurate, perfectly stable, and instantaneous glucose reading. By engineering a path straight through the enzyme's insulating shell, material scientists turned a stubborn biological barrier into an ideal analytical tool.